Hi guys, welcome back to Data Every Day. Today we're looking at a data set of New York State environmental remediation sites, and we'll be trying to predict the program type, which is a list. There's 5 different program types, based on a series of, starting with 42 columns. So you can see this has been provided by New York State. So we're hoping we can find some sort of relationship between the features that are provided and the type of program that it is. Alright, so let's get started. I'm starting by importing the usual libraries, NumPy, Pandas. Today we'll be using Plotly Express to plot our training and validation loss graphs. And then for pre-processing, we'll be using the sklearn label encoder, standard scaler, and the train test split function. And for our model, we'll be using TensorFlow. So let's go ahead and import that and take a look at our data. We'll call it data, and we'll just read it from the CSV using pandas read CSV function. And here's the CSV file, so we'll copy the file path, paste it in, and then take a look at the data. And you can see right away I can't see all the columns, so to fix that I'm just going to go into console, do pandas.set option max columns none. Now we should be able to see all the columns, and yeah, here we go. So there's first of all, a lot of missing values we can see right off the bat, and also a lot of columns. So we could probably do a lot with just a few of these. So we're going to probably narrow this down greatly. And so we'll start pre-processing, but first I'm just going to look at a bit of preliminary information with the info function, and we can see most of our data is categorical, right? Only a few numerical columns, and there's a lot of missing values, especially in this area. So let's get started by just taking a look at those missing values directly. So isNA.sum will give us the sum of missing values in each column, and we're going to notice that some of these just have too many missing values to keep, like ridiculous amounts. This one, you can see there's 74,800 rows, and this has 73,000 missing values. This one too. We're just going to drop these. Basically, if something has more than 25% missing values, we're just going to drop it. So we'll say null columns will be a list of the columns with more than 25% of missing values. This will be data.loc, all rows, and any column that has, so I'm getting this thing, no, right here, this thing, and if data.isNA.sum is greater than 0.25 times data.shape sub 0, so if a value in here is greater than 25% of the length of the data, of the number of rows, then we'll index all those columns that have that condition, and those will be our null columns. So if we run this, take a look at null columns, you can see it will be all the columns up here that just have way too many, and there's 16 of them that we're going to drop. So let's go ahead and drop them. Data.drop null columns, access 1, and data equals. Alright, let me just put that up there, and now we take another look at data. We now have 26 columns instead of the original 42, and we are working with something of an easier data set, but we're still going to have to do quite a bit of processing on this. So let's take another look at the NA values, the null values. And we can see we're left with a few, and there's going to be some unneeded columns here, right? So these guys, we're going to drop them probably, because although they have enough values, enough non-null values that we could impute them, these kinds of columns, first of all, owner name is not going to give us anything, right? In order to predict the project type, unless there are a lot of duplicates, which I doubt there are. But we can look. In any case, owner name's probably not going to give us anything. Owner address, probably not going to give us anything. Owner city may, but we can also notice that the project location is also encoded, is also contained in the county column or zip code column or locality column. So the owner stuff, if it had fewer null values, we would keep it, I think, but I think it's safe to just drop all of these because, you know, we have sort of a duplicate information from these ones up here, right? There's even an address column up here. Why do we need the owner's address when we have the address of the actual site? And so let's go ahead and create a list of unneeded columns. And there's actually quite a few in here. So I'm just going to copy it, paste it. And I'll run through a bit of why I chose these ones. Basically, program number they're all unique values. So I'm dropping program number. Project name, not going to give us, wait, where's project name? Here. Not really going to give us much information. Actually, yeah, it also has a large number of null values. So I feel there's better features to use. Program facility name, where's that? Where is it? Oh, here. Yeah, this is just basically an address, and they're all unique. So if we have a column which every value is unique, there's not really a point in keeping that column because it's not going to. There's no way to establish a pattern in the data from looking at. It's basically just an index column, right? So we'll drop that as well. Then we had the address one. This again all unique, so we're just going to drop it. Locality. This one, well, that's not really a problem, the few missing values it had, but there's a tremendous number of unique values in here. And the county has fewer unique values, not a single null value, and provides basically the same location, same information, right? So we're going to keep county, drop locality. Zip code and Swiss code, unnecessary because county sort of has that information already, and this is just going to create so many, it's very sparse matrix with way too many one-hot columns for our purposes. And right, so I dropped all the owner stuff, and then location one, which is this here. We already have, where is it? A latitude and longitude column. So as you can see, it's actually duplicate information, right? So we don't need this location one column. So I'm dropping all these, called it unneeded columns. We're just going to do data equals data.drop unneeded columns. And this will significantly reduce the size of our data set, but also make it much cleaner and easier to work with. So let's take a look at data, and now we're working with something quite manageable. So we're going to define two functions. Now what we're going to do next is try to find the categorical features and encode them into numerical features, so that everything is numerical. So as usually, I make two functions. One is get uniques, and this is going to get all the unique values of a data frame given a column, actually a list of columns. So we're going to return a dictionary that maps a column, or a column name, to a list of the unique values in that column. And that is for every column in the list of columns that we specified. Right, columns. Okay, so after that, we're going to make one more function. We're going to call it get categorical columns. And this is very simple. It just takes in a data frame, and it's going to return a list of every column. So for column in df.columns, if df.dtypes subcolumn equals object. So this is saying we're going to make a list of all the columns that have object data type. So it's just categorical columns, and then we can get the unique values of those columns to get a nice representation of what kind of data we're working with in each of these categorical columns. So we don't care about the unique values in here because it's numerical, or in these two, or in this. But all the ones that have text data, we're going to get the unique values for and put them in a dictionary so we can easily see what's going on. So I'm just first, I'll call get uniques of data, and to get the columns we want, we're going to call get categorical columns, and pass in data there. All right, and we can see, so it's mapping a column name to its unique values. First program type, you can see, has a bunch of unique values to take on no specific order, so that's a nominal feature right there. Site class, the same thing. Sorry, I misspoke. This isn't our feature. This is actually our label column. And so we're still going to encode this, but we'll use the sklearn's label encoder. We'll just map them to values from 0 to 5. 0 to 4, actually. And site class is also, this is a nominal feature. There's no order between the values, but it's text. And then county, also nominal. And you can see there's a good number of unique values, but not too many, right? We can still group. There's 74,000 examples, and they all have one of these. So that'll make it very easy to group. So the control code, also nominal. Control type, also nominal. And then this OU code, I'm not sure exactly what it means, but this is also nominal. And then the project completion date. So this one, we're actually not going to make it nominal. We're going to extract two new features out of it, which will be the month and the year. And I'm just going to scroll down. There's obviously many unique values here, but this won't be text in the end. This will be numerical. And you can see that's it. So everything we're working with is a nominal feature. There are no ordinal features. There are no binary features. Everything is going to get one hot encoded, except for the year and month columns, which I will be extracting from the project completion date column. So let's work with this date column first. Okay. If we take a look at it, right? So I'm just going to copy this in. Project completion date. It looks like this, and we have strings that look like this. So, wait, actually, right. So if I notice, if I index this string, 0, 1, 2, 3, 4, 5, 6, 7 places, I can get this. So why don't we adjust it like so? So we're going to take this, and I'll just let me mark this down a little bit. Extracting month and year features from date column. And I'll say project completion date column. Okay. So let's think about this. All right. I'm going to apply a lambda function to it. It's going to take in some x, which is one of these things, and it's going to give me back x indexed from 0 to 7. And if I take a look at that, oh, right, okay. So there's actually some null values in this, right? There's 61 null values. So I want to keep the null values as they are for now. Once we get it encoded into month and year columns, we can impute the values using the numerical data. But for now, since they're still strings, we're just going to leave the null values as they are. So what I'll say is only do this if x, if the type of x, actually no, we'll do string of x, it's an easy way of checking, is not equal to NaN. And otherwise, we'll keep x as it is. So this is the string that null values are turned into. And that should give us, right, just this string now. So cut off all this crap that we don't need. And we're now going to extract a year and a month from these. So we're just going to overwrite this column because we don't need any of that other information. So I'm just going to paste that in, and that equals this. Okay. So now if I took another look at this, we'll see we have that. So let's get the year and let's get the month and store them in two new columns. So let's apply another lambda function here. And we're still going to leave this condition on the end, right? But we're going to change this to 0 until, what is it? 0, 1, 2, 3, 4. And this would look like just the year. And then we did it again, but instead we go from 5 to 7. We'll have just the month. So data sub year will be this, and data sub month will be this. I'll just put it up here, and after that's done, we will drop data.drop project completion date from the column access. Okay, so we run this, just put it up here, and then we take another look at data. Now we have a year column, a month column, and we have yeah, I realize I actually should have made this a float, right? We can get around that. Yeah. Why don't we do that? Okay. Because we want these as floats right away, and we can just do it up here to make it easier for us. So np.float, and we'll do the same thing right here. So we're going to turn them into floats before, and I'm just going to hit run before, so it does everything. All right. Take a look. Now they are all floats. So that's helpful. Now, because they're floats, we can impute the missing values. So let's take a look at the missing values again. Data.isNA.sum. And there's actually 4 with missing values. It's these last 4, and they're all numerical. So let's impute them all at the same time. So we'll make a list, which is New York zip codes, counties, year, and month. And then for each column in that list, we're going to set that column equal to the same column, but with the NAs filled with the mean of that column. So all the NA values are going to get filled with their respective columns' mean. Run that, and now let's take one more look at this thing. We have no more missing values. Fantastic. So we take another look at our data, and everything is looking clean. We know there's no missing values here. We are ready to encode. Alright, and luckily we only have one encoding scheme to worry about, which is one-hot encoding. There are no ordinal features, there are no binary features, there is simply one-hot, which is, let's find all the unique values and make dummy columns for them, and do that for every single categorical column. So I will make a function called one-hot-encode. And you could use sklearn's library, but I like to make this function. It's very simple to write. It's like 5 lines of code or something. If you wanted, you could make it even less. So it takes in a data frame and a column. And we're going to first start by creating a copy of the data frame so we don't accidentally modify one in place. In case you had one called df, I'd like to avoid side effects. This is good. dummies will be pandas.getDummies, and we're going to get the dummies for a column. So if you're not sure, pandas.getDummies, what column can we use? We'll say, let's do site class, okay. Oh, this should be data, sorry. Alright, so this took all the unique values in site class, which are these, right, and turned them into columns. And then each example gets a 1 in the column that it had the value for. So what I mean is example 0 had a C, example 1 had a C, example 2 had an A. So down here, example 0 has a 1 on the C column, example 1 has a 1 in the C column, and example 2 has a 1 in the A column. So we're going to make dummies for every for every column that we want to encode. Here we're just passing in 1, so we get the dummies for it, store it in dummies, and then df is going to be pandas.concatenate the original data frame and the dummies. So axis 1, meaning we're just going to take the data frame and paste on the dummies data frame that we created, and then when that's done, we're just going to drop the original column that we created the dummies from. Alright, and then we'll return data frame. So this will one-hot encode any column we choose. And let's see this. Okay, we still have this function get categorical features, columns rather. Columns. And these are all of our categorical columns. Now there's one problem. Program type is what we want to predict. So we don't want to one-hot encode that. We want to label encode that. So what I'll do here is create a list called nominal features, which will just be this. And then I'm just going to remove nominal features.remove program type, because we're going to handle that one differently. And then we're going to say data equals one-hot encode data and column, or we'll say feature, for each feature in nominal features. Okay. So now, if we look at data, we have all these one-hot columns here, and the original county columns and site class columns, all those are gone. So we've converted them into one-hot columns, and you'll notice now everything is numerical except our program type column. So if we look at if we wanted to check the sum of basically count how many columns have an object data type, there's only one for a program type. And that's great. So before we go on, actually, why not just go on? We'll make a label encoder, which will just be a label encoder object from sklearn, and then data sub program type will be label encoder dot fit transform data sub program type. Alright, and that will convert each one of these to a value from 0 to 4. And if, let's say we want to get the let's get the actual mappings, we can create a dictionary called target mappings, which we will use dictionary comprehension to say, well, it's going to be mapping an index to a column for every index column pair in enumerate label encoder dot classes. So the sklearn object has an attribute called classes underscore that will return a list of the encoded classes in the order that it encoded them. So if we look at target mappings, you can see BCP has been mapped to 0, ERP has been mapped to 1, HW has been mapped to 2, and so on. So now when we get these, we'll know what we're dealing with if we want to go back. So let's put this here, and then so I think we're ready. Everything is encoded now, right? If we check this, we have 0, no more data types to deal with. Maybe just take a look at the data here. You can see this is now numerical. Everything is numerical, so we're ready to splitting and scaling our data. So by splitting, I mean let's just create an X and a Y. So Y will be data sub program type. That's what we're trying to predict. X will be data.drop program type. Everything except what we're trying to predict. Then we're going to scale using sklearn's standard scaler. And we're going to just scale X, right? We don't care about scaling Y. So X equals scalar dot fit transform X. And to maintain the indices and the columns, because this returns a NumPy array, so let's turn it back into a data frame, just so we can keep it consistent. And we'll say index equals x.index to keep it the same, and columns equals x.columns. Alright, and now once that's done, we can take a look at X. You see it's the same as it was before, but now everything, all the values, have mean 0 and variance 1. Alright, so we'll split it again now into train and test sets. X train, X test, Y train, Y test, using the train test split function, splitting X and Y, and give it a train size of 70%. Alright, and then let's just take a look at the shape of X after that. So this is what we're going to do. This is what we're feeding into our model, and then let's also get the value counts of Y. So you see we have some skewed classes, right? We have 54,000 of the examples is all in one class, and only 54 of them is in another. So, yeah, we're probably going to have to do some per class accuracy calculations, so that we're not sure that our model isn't just guessing this all the time and getting good accuracy. But I don't know. Let's see. Let's start building our model. So we're passing in. It'll be a vector of length 117. So we'll start by creating our input layer, which is tf.keras.input, and the shape will be 117, and we'll call that inputs. Then our first hidden layer will be tf.keras.layers.dense for a fully connected hidden layer, 64 activations, and an activation function of ReLU. We're going to pass in inputs. And we'll make one more of those identical, but we'll pass in X. So it's feeding through here. And then our output layer will be tf.keras.layers.dense, but with 5 5 probability estimates for each class. And the activation for that will be softmax. And pass in X. Then our model will be tf.keras.model with the inputs specified from above and the outputs specified from above. Alright, then we'll compile our model using an atom optimizer, sparse categorical cross entropy as our loss function, and for metrics we'll just use accuracy, but we will do some further evaluations later. So once that's done, let's set up a batch size. Let's make it 64, and number of epochs 60 should work. Alright, then we'll store our model's fit history in a history variable, model.fit. We're training on X train, Y train. We'll give it a validation split of 20%. Batch size as we specified, and a number of epochs as we specified. And I'm going to give it a callback function that will just help it converge, which will be reduce learning rate on plateau. And I'm just going to turn off verbose mode to keep the notebook clean. Alright, so let's let that train. And while that's going, we can set up with Plotly Express, a nice figure to plot the training and validation loss over the number of epochs. So px Plotly Express .line is going to be, we're going to plot the history.history, which is this thing's history attribute, and we're going to plot two values from that, two lists, one being loss, one being val loss. If you don't know about Plotly Express, it's a very nifty library to use when you want simple plots that you just whip up really fast. This is just one line of code that's going to generate the entire plot for me. So our labels will be a dictionary that we map index to our x label, epoch, and value will go to loss. Let me just, okay, oh, this should be epoch. Alright, and then title will be training history, or we could say training and validation loss. Alright, and this is finished. So we'll say fig.show. And we can see it has converged nicely. Looks pretty good. Let's get some results. Oh, well, this would actually be in results. So let's move that down under results. And then let's get let's evaluate the model just on the test set, right? Model.evaluate, see how it did on x test, y test, and we get an accuracy of 99%. So that sounds really good. We have one problem, which is this guy. We don't know if we can accurately classify this, and it's possible that we don't even have one of those in our test set, because we have 74,000 training examples, and the test set is 30% of that. It's very probable or possible that none of those 54 labeled examples could end up in the test set. But we're going to try to get accuracy values for each class. So to do that, we're going to iterate through the labels, which will be range of 0 to 4. So for each value in 0 to 4, we'll create the indices of test examples that have that label. So ytest if indexed at all places where ytest equals label here being a value from 0 to 4, and dot index. So this is all the indices where our test examples have the given label. Then our label accuracy will be model.evaluate xtest indexed at label indices, and ytest evaluated at label indices. Alright, just turn off verbose mode, and then we're going to print fstring class label accuracy let's put it here, label acc sub 1. If we index at 0, we get the loss. If we index at 1, we get the accuracy. So, alright, print that. And verbose, it didn't actually set it. Okay. And very nice. Very nice. Okay, the one thing we can see is that class 3 only has 81% accuracy, But what's very interesting is that class 4 has very good accuracy. So when I was running this before, my class 3 got 96%. So I think this model, this also is only 3,000 examples, so it's possible that not enough of these ended up in the test set. But you don't know. I actually think this model is performing very well for what we were given. I was not expecting to get such high accuracy values, because I guess that the program type is actually quite dependent on these features. And we cut out a lot of features. We started with 42 features, and we probably broke that down to about 10. Then we hot encoded it. So we ended up with 117. But you get the idea. So I think that wraps up today's video. Thank you so much for watching. If you enjoyed it, make sure to subscribe and hit the bell, and leave any comments in the section below. I'll see you guys tomorrow. Have a great day.